Subchapter 6.4 Dual Combustion Engine. Due to modern engine operates at higher speed, dual combustion engine is more suitable cycle for compression ignition engine. In dual combustion cycle, the heat addition process is comprises of constant volume process and constant pressure process. If we refer to the PV diagram, the heat addition processes is as it is a combination of both Otto and diesel cycle. For dual combustion engine, generally it have four main processes which are compression, heat addition, expansion, and heat rejection. For heat addition process, there are two processes involved: constant volume heat addition and constant pressure heat addition. With respect to the PV diagram, process 1 to 2 is the isentropic compression. We can use the isentropic relation to find the required properties in this process. Process 2 to 3 is the constant volume heat addition. For this process, we can use the relation of P2 over T2 is equal to P3 over T3 to find the required properties. Also, we can determine the heat transfer Q in for this process. Since process 2 to 3 is a constant volume process, the heat transfer for process 2 to 3 can be determined by using the equation of Q in is equal to mCV times T3 minus T2. For process 3 to 4, it is the constant pressure heat addition process. We can use the relation of V3 over T3 is equal to V4 over T4 if we want to find the related properties for this process. And we can determine the heat transfer for process 3 to 4. From the non-flow energy equation for a constant pressure process, we can obtain this equation. Process 4 to 5 is the isentropic expansion process. Since the process works isentropically, we can use the relation of isentropic process to find the properties during this process. For process 5 to 1, it is constant volume heat rejection process. If we want to find the properties between this process, we can use the relation of P1 over T1 is equal to P5 over T5. We also can find the heat that is being rejected during this process. For constant volume process, since the process rejecting heat, we can obtain this expression. Thus, the heat that is being rejected by the process 5 to 1 is being given by mCV times T5 minus T1. For the total heat addition, it will be given by the total heat transfer in is equal to heat transfer during the process 2 to 3 plus heat transfer during the process 3 to 4. For the thermal efficiency, we can determine by using these formulas, or we may derive to this expression.